Hello, today we're going to talk about electrolysis and Faraday's law. This is the last section in all of the 9 units of AP Chemistry. I will also be making some review videos for each unit to help prepare for the AP exam in May. Okay, so let's talk about electrolytic cells. I've mentioned them before, but just to review, electrolytic cells, they must have a power source. Because if you were to hook it up in the same direction, it would be non-spontaneous, not thermodynamically favorable. So it would not happen. You have to apply a power source to force it to happen in a direction that it doesn't typically want to. So their standard cell potential would be negative, and their delta G would be positive for this. Let's look at a typical kind of drawing of an electrolytic cell. I'm going to do my best. We would have 2 beakers. It's going to look very similar to a voltaic cell. So you have your metal electrodes submerged in a solution of their ions. You'll need some kind of salt bridge, or it might be like a porous membrane between the two. And then you would have to hook up to a power source. Typically, they'll indicate like that it's a battery or that it's plugged into some kind of power source, but in some diagrams they'll use this symbol here where it is showing that means a power source is being applied. I'm going to draw it with a battery just to make it really clear that that is a source of power, right? That is what's driving this reaction. Now the battery itself is what's pushing the electrons through and creating an electrical current. We're going to look at factors including current, charge, and time that you apply the power source, because all of that has an effect on how much that electrolytic reaction can happen. And we call electrolytic cells the reaction that happens, and that we call that electrolysis. And it can result in some really interesting things. A big one that you should probably know is called electroplating. So have you ever heard of like gold plated or silver plated or chrome plated, chromium plated, right? That all happens via electroplating. So where you would take a piece of metal and you would submerge it in a solution of, say, gold ions, apply a current, and then the gold metal plates or coats the piece of metal, so you have a gold-plated thing, right? But you have to apply a power source to make that happen. It's very cool. So let's talk about current. Electrical current is the amount of charge that is transferred over time, and we use the letter I for current, and it's measured in amperes. Sometimes I'll just say amps. The abbreviation would be A. And an ampere, let me write that better, ampere is equal to 1 coulomb per second. So I say 1 ampere is equal to 1 coulomb per second, for every 1 second. You need to make sure that when you're doing problems involving this, that your time is in seconds. That's one of the biggest mistakes that I see, is people will leave it in minutes or hours or whatever. Make sure it's in seconds, because that's how amperes is defined. All right, so effectively, that turns into your current I is equal to your charge in coulombs over your T, your time in seconds. So we can use that to find the charge. Or if you're given the charge, if you're given the current, rather, you can find the charge by multiplying it by time. So this equation is given on your formula sheet, but I would say you would use either form pretty equally as frequently. Okay, we've used Faraday's constant before, but in this section it's actually kind of important to understand what Faraday's constant means. So Faraday's constant F is equal to 96,485. That's the number. It's on your formula sheet. You don't have to remember it. But the unit for it, you should remember, is coulombs per second. I'm sorry, coulombs per mole of electron. I was getting my equations confused. Per mole of electron. Coulombs per mole of electron. So Q is measured in coulombs. That is the quantity of charge. Coulombs. And we know that I equals Q over T. We can relate the current to the moles of electrons, and therefore our chemical reaction, using Faraday's constant. So it winds up being very, very useful. Okay, so it says what mass of gold in grams is plated by a 20-minute flow of a 5.5 amp current. And it gives us this equation for the gold. That way we know that there's 3 moles of electrons being transferred. Now, the first thing I would say whenever you see a question like this is you want to change minutes to seconds. Okay, so I have 20 minutes, and I know for every 1 minute there's 60 seconds. Okay, so I'm going to set this up as one big problem. You can break this up into smaller pieces, do each one individually, that's fine. But we can cross out the minutes there. Now I have seconds. We know that amps is coulombs per second. So I know for every 1 second there are 5.5 coulombs. Oops. Coulombs. That's what amps means. So now I can cancel out the seconds. Now that I have coulombs, I have the Q, the charge, I can use Faraday's constant. It is 96,485 coulombs for every 1 mole of electrons. From there, I can use my balanced chemical equation to find the moles of gold. So I would do, there are 3 electrons for every 1 gold atom plated. And my last step, I'll have to stick it down below, so the electrons are canceling. My last step is I want to change to grams because it's asking about mass. So I just need to use the molar mass of gold. So I would do the molar mass of gold is 196.96 grams per mole for gold. So our moles cancel now. So I would do all of this together, 20 minutes times 60 times 5.5 divided by 96,485 divided by 3 times 196.96. So all of that all at once. And you get 4.5 grams of gold. And again, feel free to break that up into pieces if you want. It's fine. You don't have to set it up as a giant dimensional analysis, but please make sure you are using dimensional analysis so that you know which units to use when. Okay, so here's another example. Calculate the charge transferred, so charge is Q, in a reaction that uses 2.5 amperes. So that's Q over T. Ooh, that's a G, Q over T. For 5 minutes. 5 minutes. Uh-oh. 5 minutes, we need to change that to seconds. So you would do, I'm going to do this in separate steps this time. 5 minutes times 60 seconds per 1 minute. That's 300 seconds. And then I know my amperes, it's equal to Q over T. We're looking for Q. We know our time in seconds is 300. Multiply both sides by 300, you get 750. And my unit for charge is coulombs. So the quantity of charge for 5 minutes of 2.5 amps is 750 coulombs. Now, it says tin is used as a cathode in the following chemical reactions. So that cathode is reduction, and it is written as reduction, so that's good. Now it says if 1.34 grams of tin is plated onto the electrode over 75 seconds, what current must have been used? So this one is working a little bit backwards. We have the 1.34 grams of tin. I need to change it to moles. So its molar mass is 118.71 grams per mole. And then in my equation, I have 2 electrons for every 1 tin. So the grams have canceled, the tin has canceled. Now I have moles of electrons. I can use Faraday's constant because Faraday's constant is 96,485 coulombs for every 1 mole of electrons. So the moles can cancel and electrons cancel. So now I have coulombs, that's Q, that's our quantity of charge. I can use the time. I'm going to put that on the bottom, 75 seconds on the bottom, because amperes, ooh, I wrote that backwards, amperes is coulombs per second. So I already have coulombs on the top, I need seconds on the bottom. They won't cancel because that's what I'm looking for. So to calculate, you would do 1.34 divided by 118.71 times 2 times 96,485 divided by 75, and you get 29 amperes, which you would apply over 75 seconds if you want 1.34 grams of tin.